Great. Well, I just wanted to start by thanking the organizers, especially to Andre for stepping in at the last minute when I missed a connecting flight and wasn't able to speak on Monday. So that was really nice. Okay, so this is joint work with Chris Rycroft is a postdoc working with Jamie Sethian and me at UC Berkeley and LBNL. So all the 3D work he's the one who coded it up, and all the 2D stuff I coded up. Mostly I'll be talking about 2D since I know that work better. Okay, so I want to start by talking about a really interesting and famous conjecture of Stokes about the form of the largest amplitude traveling water wave. So what you're looking at here is a nearly, something very close to the largest amplitude water wave, where you just have a Stokes wave moving to the right, so it's an irrotational, incompressible fluid. I put the markers there just so you could visually see what's going on in the flow. My numerical methods don't involve those particles. It's just for visualization at the end. And what you see here is, Stokes, using an asymptotic expansion of the stream function near the crest there, decided that the limiting wave profile, so you could continue to increase the amplitude until a 120-degree sharp corner appeared, and then beyond that, you wouldn't be able to get a larger amplitude traveling wave. So this was proposed in 1880. It took about 100 years for somebody to prove it. So Amick, Frankel, and Tolan proved that in 1982. And a few years before that, Longwood, Higgins, and Fox thought about the matched asymptotic analysis of this problem for the almost highest traveling wave, which is also an interesting story. It turns out it is it approaches in a self-similar fashion, but in an oscillatory way. So if you look at the inner solution in this matched asymptotic expansion, it turns out that the inner solution crosses the asymptote an infinite number of times. So as you approach that limiting wave, it doesn't actually approach this nice 120-degree wave in quite the smooth way that Stokes probably had in mind. But nevertheless, it does so, and it does so in a self-similar way.
So what do you mean by it took 100 years to prove it? That the wave actually exists? Or, that it's up above?
Well, first of all, that the limiting wave with an actual corner there does satisfy the equations, and the corner actually is 120 degrees. Stokes is just sort of guessing. He's just writing things down and sort of using back-of-the-envelope calculations to say this is probably what happens. These guys rigorously wrote down like an integral form of the water wave equations and showed that the solution of this is actually this wave, and talked about what the form of the shape is connecting the singularities and so on. But, okay, so
Is that wave...
Sorry. Oh, go ahead.
Is that wave supposed to be unstable?
This wave, is it supposed to be unstable? If Dave Nichols were here, he would tell you that in his talk. I'm not sure. I think that it may be... That it's unstable?
Yeah, this is really...
Okay, well, let's not get into that. I'll talk about stability of this later in the talk. So in the 50s, so long before the Stokes conjecture had actually been proved, Penney and Price proposed that the largest amplitude standing wave would have a similar thing, but instead of 120 degrees, it would form a 90-degree corner angle. And this is a picture from their paper on the right here. So basically, this is what they had in mind would happen as the wave sloshed back and forth. And what they did there was, I think it was a fifth order asymptotic expansion in powers of the amplitude. And then I have no idea how they came up with 90 degrees at the end. And actually, neither did G.I. Taylor. G.I. Taylor read their paper and said, I have no idea what they're talking about. But he actually did manage to do an experiment and try it out. So G.I. Taylor built this really impressive wave tank machine where he sloshes the sides in and out, and this causes, at basically the resonant frequency, this causes the waves to grow in amplitude. Then he took photographs of them, and they really do come to about 90 degrees. So he said, I have no doubt that it's true, but I don't know what they're talking about, basically, in their derivation. That's more or less what that paper is. So then the question is, okay, so it seems to happen in the wave tank. Of course, it's going to be very hard to set up something that exactly meets at 90 degrees. And all of his waves start to splash right at this point, and actually they lose stability in the transverse direction if he tries to increase the amplitude beyond this. So that's experimentally what the story is. And so I want to ask the mathematical question, if you go back to the true equations, what is the limiting wave profile? What's going on here in this problem? Okay, so prior to this work, I had been developing a lot of methods for solving two-point boundary value problems. So this is where you try to, you have a nonlinear evolution equation. you want to say something about what happens at the beginning and what happens at the end. So there's 2 points in space, and in between you have to solve a PDE. So I've been developing methods for these kinds of problems. We've applied them to the Benjamin-Ono equation, which is, so some of this is joint work with Dave Ambrose at Drexel. So he and I wrote a paper on the Benjamin-Ono equation, actually 2 papers, and then we applied our method there using adjoint-based optimal control algorithms to solve these boundary value problems for the vortex sheet. And then I sort of split off and started working on this standing water wave problem. The new approach is quite different. I was doing, I think, a 4th order time stepper in the previous approach. Now I'm doing 8th or 15th order. 8th order is still just a plain Runge-Kutta method. The 15th order time stepper is a spectral deferred correction method. And as you try to really push accuracy, every bit of order helps a lot. So 15th order turned out to be necessary to prove or to compute some of these things. It's very fast. Everything's parallelized. I'm actually using a GPU now to do the computations, which has sped things up quite a lot. And my approach here in doing these boundary value problems is very different than previous approaches to standing waves, which have been computed by other people before. Mostly it's more robust because I pose the problem as an overdetermined problem. So, like you have 1,500 degrees of freedom at the beginning, and you have 8,000 equations you're trying to solve, and somehow that causes those 1,500 that you're looking for to be very accurately determined, or very well determined. And I'm sort of currently trying to figure out a good hybrid approach between this has no adjoint method in it. I'm not solving anything backwards in time. I compute the full Jacobian. Here we sort of go forward once, backwards once, find the gradient, and then sort of step through space using a BFGS method. The problem with that is that it's hard to parallelize well. The problem with this is that you compute the whole Jacobian, and it would be nice to just compute a few columns at a time. So that's sort of where I'm at on the numeric side. The equations, the way I'm formulating the standing wave problem, this does not overturn, so there's no reason to go to a complicated thing that allows for overturning waves. So I'm just using sort of the classical Stokes formulation of the problem. You have here you have a kinematic condition that says that particles on the surface stay on the surface. Phi is the velocity potential, so U equals grad phi. And then this is just the sort of unsteady Bernoulli equation integrated once. One thing I do here is I have these 2 versions of phi, which is terrible notation, but it was too hard to change in all the slides. So this lowercase phi, or this var phi thing, is the restriction of the 2-dimensional phi to the free surface. And then I would like to essentially eliminate what's going on in the bulk of the fluid. And so you do that by, that's sort of what is going on in these equations. And that's the Dirichlet-Neumann operator. So this is an evolution equation in eta, and in the restriction of the velocity potential to the free surface. And at every time step, you have to compute this Dirichlet-Neumann operator, which tells you basically what are these derivatives, or what are the velocities on the boundary given what the potential is on the surface. So that's how this method works. It's essentially a 1D problem, except that you have this 2D constraint living on the side. And once you know, so essentially what you need to figure out is what is the normal derivative of the velocity potential at the boundary. Because you already know the tangential derivative, you can just take a derivative of var phi along the boundary. Okay, so this is how you would get the velocities once you know the Dirichlet-Neumann, or the Neumann data along the boundary. So everything boils down to being able to solve this Dirichlet-Neumann operator in terms of what makes these equations hard. So I'm doing a boundary integral collocation method to do this. So I represent the curve by this function zeta of alpha. In 2D, it's very convenient to work use complex variable methods. Certain things turn out to be beautiful when you sum over periodic images. You'll end up with like a complex cotangent. So here's our curve, zeta of alpha t. You could just parameterize that as zeta of alpha equals alpha plus eta of alpha. But I want to be able to respace the grid so that its grid points are closer together near the singularity, or near the crest. So I introduced this xi here for respacing to do adaptive mesh refinement. And then eta is still just our function eta of x. So if I write down zeta like this, I write down phi as a double layer with respect to, so this Newtonian potential is sort of the standard log potential. You can sum this thing over periodic images using complex variable methods. And it turns out you just end up with a cotangent instead of a 1 over z as the building block of your solution inside of the fluid. You're distributing these guys around the boundary to figure out what phi should be. So ultimately, the formula for the velocity potential phi there in the interior of the fluid is just an integral against an unknown moment mu, a dipole moment on the surface, and then the kernel of this thing, k, just involves the imaginary part of cotangent times zeta prime of alpha. And cotangent is evaluated as like the distance between zeta minus z. So that's it's a very beautiful formulation of the problem. I'm not the first to do that. I mean, I think it goes back at least to Baker, but I'm sure people even knew how to do these complex variable methods for free surface problems before him. That would have been in the 80s. Okay, so the equations that you have to solve at every time step to figure out the phi x and phi y, so the Dirichlet-Neumann operator. You know phi at the given time, so that's what this phi of c of alpha is. You're trying to figure out what mu is, what the density is in your formula for the velocity potential in the interior. So this is a second kind Fredholm integral equation for mu in terms of the known phi. You discretize, so this delta, this 1/2 thing comes out when you take the limit. It's from the Plomelli formula, or if you think about it just in terms of the potential theory, it's what you get with a double layer potential as you approach the boundary. So that's the 1/2. That makes this a very well posed problem. Unlike finite differences, which get much worse and worse as you refine the mesh, the condition number here basically stays order 1, no matter how many mesh points you use, which is a huge advantage of boundary integral methods. So you solve this equation. What you do is you discretize using uniform grid points in alpha. You just evaluate this matrix K. That turns this into a discrete system. You solve that for the mu's. And then you take one derivative of mu with respect to alpha. That's the place that this operator becomes unbounded. Everything else is nice. And then you reconstruct the normal derivative in this way. So there's only one thing that's sort of bad, that amplifies errors in this procedure, and it's just taking a derivative. So that's a pretty nice system. If something's going to be bad, it might as well be just taking a single derivative. So the way we actually compute this is probably the best problem you could possibly put on a GPU. You send in a one-dimensional thing, that's phi on the boundary and eta on the boundary. It computes in O of n's. It looks at all pairs of these values and computes complex cotangents of them, and it stores them in a matrix. You just leave that on the GPU, so that doesn't have to come back to main memory or anything. Then when you need to solve the equation, you send the GPU when eventually you have to solve for mu. You ask the GPU to solve this using GMRes, but you're only ever sending back and forth one-dimensional arrays of things. The GPU is doing O of n squared things or O of n cubed things, but it doesn't have to be moved back and forth. So that's the biggest problem with GPUs usually, is just transferring the data over there. But in this case, basically this makes it, I think, faster to solve the water wave than it is to solve like KDV, because it's a better posed problem, and you've pushed all of the expensive stuff onto hardware that can do it very fast. So I feel like eventually solving the full Euler equations is going to be as easy as most of the model problems that people are deriving to study them. Ultimately, you have a matrix equation here. I solve this by GMRes if I'm just evolving the equation. If I do the Jacobian, I'll actually factor this thing once and then do lots of right-hand sides over and over again, which ends up being very fast. Okay, so that's the idea. You can parallelize it very well. It's not that hard to parallelize on the GPU. You're literally just running through computing that those cotangents at all pairs of points. Okay, so how do you compute time periodic solutions? I've just told you how you would evolve, given any initial condition, how you evolve forward in time. And now we want to find appropriate initial conditions that will actually, so that the solution will repeat itself at a later time t. So what I do, and I think this is annoying, part of the slide t is going to be a quarter of the period, and part of it's going to be the whole period. So sorry about that. But here what I'm doing is, if you can start with appropriate initial conditions, and you can make the velocity potential be 0 at a quarter period, and you have the right symmetry at the beginning, then once it stops, I mean, that means that the water wave has completely stopped. It will come back, essentially reversing time from that point, and come back. All that will change when you get back to 0 is that the velocity potential will change sign, and then it will go back as if you had run it in reverse to the opposite standing wave going out, and eventually it will come back again to where it started. So this saves you a factor of 4 in computing time. You only evolve over a quarter period, and what I'm trying to do here is minimize the I'm trying to make the velocity potential be 0 at this later time t, which currently means a quarter of the period. The initial conditions that we want, it turns out you want eta and phi both to be even functions. And not only that, you want them to have certain translation properties where if you translate eta by... Oh, yeah, sure.
It doesn't necessarily follow, right? I mean, if you have a wave that goes to the maximum,
Yeah.
comes back to 0, and you don't compute the bottom part of it,
Yeah.
it could be that it goes singular at some point.
It-
Because it's not symmetric.
Oh, well, that's what these initial conditions are required for this to work. If you start at 0, where phi is 0, and then at a later time phi is 0 again, you'll have a periodic solution. I'm cheating even more than that. I'm starting halfway between the two places where phi is 0, and I've set it up so if I were to go backwards in time, I'll get 0 as well. So this is a way of ending up with phi being 0 at 2 points in time, not either of them being at time 0. So these are the variables. You also don't know the period in advance, so that's one of the variables that we try to solve for. And you set the Fourier coefficients of phi and eta up in a way that this will happen. If you go backwards in time, you'll hit phi equals 0, also at time minus t, I guess. All right, so that's how it would work. The details of the particular way I'm solving this thing, I'm trying to minimize this using something called the Levenberg-Marquardt method. Levenberg-Marquardt is a nonlinear least squares solver. So you have lots of equations. They depend nonlinearly on, in this case, the variable c, which is a big vector. And so what you need to write it in the form of 1/2 r transpose r if you're going to use Levenberg-Marquardt. In this case, this is an integral of the square of something. So you can just discretize that integral using the trapezoidal rule, which is spectrally accurate if things are periodic. And so this is the residual that we want, and the square root of e nu thing has to do with my respacing of the mesh points. So basically what you've done is you've discretized this integral in a way that it looks like r transpose r, which is what Levenberg-Marquardt wants. And this is my so I have a very naive adaptive method. I decide where do I change my grid, and I also decide how closely spaced will the grid be. And I'm doing this in a smooth way. So I'm sure this is incomprehensible, this equation here, but the idea is that you cause the mesh to be more closely spaced at pi than at 0, and the sign here just is sort of the shape of the spacing of points as you go. So if that sign dips down close to 0, it means the mesh points are very closely spaced. So that's all that is. And I'll show you a picture of E later on. Okay, so, and also, in terms of numerical continuation, it turns out that I'm allowed to specify one of these degrees of freedom in advance. And then the method will solve for all the other degrees of freedom. It will minimize over all the other degrees of freedom without changing that one. So I use one of these C's as my bifurcation parameter, and the rest of them are solved for by the algorithm. And you often have to switch which C you're using as you encounter turning points and things in that particular parameter. So here's an example. This is I should stand over here. So what I've done here is taken C1 as the initial bifurcation parameter. I varied it in the negative direction. I don't remember why I did that. I think that's the one that causes the thing to go toward the center instead of going away to the sides at the beginning. So I vary this parameter down. Each dot on this curve corresponds to a time periodic solution. So the solution y is shown here, evolved over a quarter period. You keep going, the solution z is evolved over a quarter period. It gets sharper. If you keep y and z, I started at a and I needed to go backwards. So I just wrapped around in the alphabet. That's what that is. Okay, so what I will eventually show you is what's going on beyond A. Up to the point A, everything's very nice. And so this solution A is more peak 2, and I think this is maybe the movie. I think actually something that's going to be called B later was the movie I showed you initially. But that's the idea. You change this C1, you solve for T, and you solve for all the other C sub Ks, and then you plot them. You make a plot of them. What has been done in the past, I think Mercer and Roberts were the first to do a really solid computation of standing water waves. This is in the early 90s. And they defined a parameter called the crest acceleration, which is when the thing reaches the stationary point. The question is, to what extent are the particles just falling freely at that point? let's see, Penney and Price thought that the wave amplitude would be a good choice for the sort of parameter describing the bifurcation family. Mercer and Roberts showed that actually wave amplitude eventually stops increasing and starts decreasing, so it doesn't change monotonically over this family of solutions. So they proposed using crest acceleration instead. That's what's been done in all the papers since, which is probably about 15 papers or so of people computing these things. And so that's the standard thing to plot on the bottom axis is this crest acceleration. And the idea is that the more singular the thing is, the faster the smaller the pressure gradient is up there, and the closer you are to just free falling. And so they think that that should be the parameter that should be used to sort of say how far along the bifurcation curve you've gone. And you can see that my C1 was a great choice for a long time, but eventually it turned around. And so it would be bad to use C1 anymore and to try to track these solutions around that curve. So at some point I switched to C6, and then I can very nicely, C6 is changing monotonically in the region where C1 had the turning point, so I switched there. And in practice, it's pretty easy to identify one of these guys that's changing monotonically. Yeah?
The original conjecture was that this without surface tension.
Without, and I have without as well. Vernenbrock and a lot of people have thought about the surface tension problem. I've computed it. I'll show you some pictures there. But things change quite a bit when you add surface tension. So the original conjecture was that there would be no surface tension. And so that's what most of my talk is the no surface tension case. So I should say maybe something about how Levenberg-Marquardt works. What you do is you approximate your function you use a quadratic approximation for your function. You use the actual gradient, but you don't use the actual Hessian of the function. And what you throw away, so these formulas are all exact. The Hessian is well, if B is J transpose J, where J is the Jacobian of R. Remember, you're minimizing 1/2 R transpose R. That's what F is. J transpose J is sort of the main part of the Hessian, and then there's this other part that's like R times the sum of Ri times the Hessian of each Ri. Because those Ri's are being driven to 0, this term eventually goes to 0, and it ends up being a quadratically convergent minimization algorithm for 0 residual problems, which we have here. So that means this works like Newton's method, except that I can have a lot more equations than unknowns. It will still converge quadratically if the R's go to 0, because the term you're neglecting in the well, actually, I probably should go to the next slide. The term you're neglecting is going to 0 as you converge to the solution. So the linear algebra involved in minimizing this, where you replace the true Hessian by J transpose J, ends up being a system like this. It's a constrained linear least squares problem. What you're doing, so the trust region means that you have a parameter delta over which you think that your function f is well approximated by this quadratic approximation within p less than delta. And so to minimize over that region, you introduce a Lagrange multiplier. If the Lagrange multiplier is 0, then it's an unconstrained problem, and your minimum will lie inside of the trust region. If that's not the case, if the minimum is outside, if the Hessian is well, I guess it can't be indefinite if you're just using J transpose J. In the more general case where you do an indefinite Hessian approach, this parameter lambda will pull the point onto the boundary of the trust region. And so all you end up having to do is solve this nice system where you have J and then lambda times the identity, and you solve this using sort of a standard linear least squares. And there's a nice algorithm for computing what lambda needs to be, which also converges quadratically. So it's a very robust method. The main thing that's nice about it is I'm never computing J transpose J. I'm just dealing with J. So I don't square the condition number of J right off the bat. And that's why this method is great. It's very hard to improve on this in terms of accuracy, because as soon as you try to add additional corrections to the Hessian, you can no longer sort of break it up into just dealing with J. And you end up squaring condition numbers. Small things become tiny. Large things become big. So this approach is great for this if you have small residuals. And then you change delta at each time step, because after you've made your guess, you have the value of the approximate function f, and you also have the value of the actual f, at that next time. And if they're basically exactly the same, then you say, oh, my trust region was too small. I could have taken a bigger step. So that at the next step, you use a bigger trust region. And if they're wildly different, or if it simply fails, like you thought you were going to get a smaller value and you get a bigger value instead, then you decrease the trust region and try again. So it's a nice algorithm for minimizing least squares problems. You have to have the Jacobian there. I have this J transpose J. I compute the Jacobian by solving linearized problems around the current solution. So we have our standing wave. It's currently not it's not a standing wave, actually. You have a guess for the initial condition. You evolve it. It's not a standing wave. You have your guess for the time, too. That function f tells you how bad a jaw, or how far away is it from being a standing wave. And then you could say, what would a perturbation of the initial conditions do to my objective function f? And so that's what this Jacobian J does. Whatever perturbation I make of the initial conditions, multiply by J, that will tell you how the solution phi changes out there, and then you can use that to figure out what the gradient of f is and what to do in the algorithm. And so just very briefly, if this is our equation, qt equals f of q, that representing this whole mess, then the equation for q dot is just q dot t equals df of q dot. So you're linearizing around q. And in this case, there's sort of an interesting complication that phi, you're evaluating phi here on a boundary which itself moves. So you have to take into account that actually these guys are being evaluated on the boundary eta, and when eta changes by epsilon eta dot, that also introduces terms from the chain rule. As long as you get that straight, it's pretty easy to compute this Jacobian. So the Jacobian amounts to solving a problem very similar to the water wave problem, except that the kinematic condition is a lot more complicated, and the sort of fluid mechanics equation almost looks unrecognizable. But the main point is that this part is exactly the same. It's still a Dirichlet-Neumann map. And it's the same Dirichlet-Neumann map for every column of the Jacobian. So you only have to set up that data structure once, and you can use it over and over again for every column of the Jacobian. Which means that, Paul asked me if I worry about cache issues in my computations. Not so much, but I definitely worry about sort of reuse of things. And here I compute this matrix K once, I factor it once, I solve it for every column of the Jacobian at the same time, which means that you can go through about 100 columns of the Jacobian in the cost of doing one water wave solve. So the forward problem of the water wave, you can compute 100 columns of the Jacobian in the same amount of time. So if you need 1,500 columns of the Jacobian, it's only 15 times more expensive than just evolving the water wave forward. So that's where this method of linearization is better than previous methods of you can differentiate the Fortran. There's lots of other ways of doing shooting methods, but by linearizing, you get this savings where you have the same Dirichlet-Neumann operator for all the columns of the Jacobian, which makes a huge difference. And also, you sort of go into Jim Demel's world and do all these things at the computer's maximum speed, these plops. All right, so now let's get back to the question of the limiting wave profile. So here are three solutions. A is the one I showed you. That was the last one on the curve. B is a little bit further along. C is a little bit further along still. Things are definitely looking like they're sharpening up, but C is starting to break from the prediction. So this is Mercer and Roberts' result. They're the ones who realized that eventually the wave steepness h, which is I think half the crest to trough height, is not a monotonic function and starts to decrease. And then I have shown that, in fact, neither does crest acceleration. This curve that seemed like it was going to nicely go to 1 there and have some limiting wave profile has a couple of turning points in both variables and fragments into all kinds of pieces. So the problem just gets very messy as you try to approach that limiting wave. It's nothing like people thought. And you might think, people are wondering, well, it's probably your numerics that are wrong. So currently we're doing the crest acceleration here versus the wave steepness here. So you see, if I think about this as crest acceleration, it's right in this region. The crest acceleration actually starts to decrease. And so you can't just monotonically change that and increase all the way to 1. here's the variables I actually used. I think I only used these three, C1, C5, and C60. So as you're moving along that curve, at some point, around point E here, the solution got so complicated I couldn't continue it, but it looked nothing like the Penney and Price standing wave. And my numerical method sort of accidentally found a couple of other branches. And so every time I find a new branch, I track it in both directions and occasionally land on new branches. So this is the main plot on the outside here is the 60th Fourier mode versus the crest acceleration. And actually this was the bifurcation parameter. I'm plotting this against that. This was the first one. This is C1. That's the one I used to get most of the way. Then I switched to C5. I used that to get sort of through the turning point of C1. And then I found C60 does a nice job of separating out all these things. So there are all these they're certainly disconnected families of solutions. Is that clear? Sometimes I think I put too many plots on.
You do this in double?
I do this in double. I did all of these guys in double, and then I think, where do I do some things in quadruple now. And I'll show you, I use the quadruple to test the double, and I can minimize in quadruple, but not quite as far out on the curves. Okay, so this is that curve that I showed earlier, and here I'm zooming in on various pieces of it. So this is nothing like what Penney and Price expected. It's nothing like all previous numerical studies expected either. In fact, some of them actually draw these beautiful curves that go right down to 1, and then they show a 90-degree angle, which is really interesting because it's just wrong. I mean, by the time they get to point C, there's no longer any resolution in their code. They're using like 256 modes, and I'm using 9,000 modes. And you need 9,000 modes to get past that spot. So anyway, it's interesting that an under-resolved solution will so nicely look self-similar.
You have no surface tension,
Right.
Going to the point where the effect of gravity at the surface becomes zero.
Yeah, basically.
Storing mechanism left, so you can have any wrinkle.
Exactly. Yeah, that's what happens. That's right. Okay. So let me just show you how things go wrong then. I mean, maybe Oliver wasn't surprised that the Penney and Price conjecture was wrong, but instead of sort of sharpening up and becoming self-similar, this is solution A. It looks pretty, well, I guess I've zoomed in so much it doesn't look pointy at all, but it does if you scale out. This is 0.99 pi to 1.01 pi. As you move along these curves, you end up with these higher frequency oscillations that show up right in the vicinity of the crest tip. The other thing that's interesting is that overall there's this sort of almost jet of fluids popping up at the crest, which looks just like what Taylor saw in his experiments. And Vandenbroek decided that was probably because of surface tension. So he wrote a paper saying that only happens if you have surface tension. It turns out it also happens without. And it's just sort of like, I think, well, I'm not exactly sure why this jet occurs, but it seems to be a pretty robust thing. Once you get beyond about 0.99 of gravity, you'll end up just shooting up this little burst of fluid at the top.
So when you say 200 times the resolution figure, does that mean global resolution or the local?
That's the local resolution. The global resolution, I think, is about 30 times or so. I should be able to do the arithmetic. 8,000 divided by 256, whatever that is. Okay, and here are the slopes. So solution A, solution B is sort of, so here's 1. So that would be sort of like a nice 90-degree angle would be if these slopes sort of eventually approached like a Heaviside function here that drops straight from 1 to -1 at this point. A, B, and C are kind of looking like they're heading that way, although C has already overshot 1. By the time you get to D, things have gone up, and then it's flattening out here instead of sharpening. And then by the time you get to E, you get these oscillations. And this is all of the solutions, and this is just the ones on basically that first branch before there's a disconnection in it. So this is showing that resonance is sort of somehow taking over instead of the thing becoming self-similar. All right. Yeah, sure. So like all of my double precision calculations, energy is conserved to between 12 and 15 digits, depending on how many. As the system gets bigger, there's more effective round-off error. It might be my next slide. Okay, accuracy check. So here's the solution. So the first 4 times, let's see, t equals 0 up to t equals 4. Most of these guys are on this graph going from 0 to 0.5. The last one here is on this graph going from 10 to the minus, or 2 times 10 to the minus 12 up to, well, it's on the order of 10 to the minus 12 over here. And the value of the function f is 10 to the minus 26. In this calculation, energy was conserved to about 13 digits. I then redid it in quadruple precision. Now energy was conserved to 25 digits, and I refined the mesh as much as I could before my GPU runs out of memory. But you can see, like, even this crazy structure right in the middle is actually resolved. You probably can't see those dots, but all those oscillations have about 15 points on them. So like, this is taking the initial conditions I got from double precision and then running them in quadruple precision and just seeing how accurate is the solution. So now I actually have the value of f, which is correct, because this thing is resolved in the quadruple precision calculation. So weird. This almost never happens, where the true f is smaller than the one predicted in double precision. The reason the f here is not so accurate is that you've tried to eliminate all the significant digits of phi from your solution in the minimization. So what's left is almost garbage. I mean, it's just this value of phi there that you've canceled all the significant digits at the beginning to make this be the value of phi at the end. But here we actually resolve that final value of phi, and the actual value of f is still 10 to the minus 27. I've also done it where you do the minimization in quadruple precision, but I can't come anywhere near to 9,000 degrees of freedom in that case. But for solution A there, which only had 1,000 sort of essential degrees of freedom running around, I got f down to 10 to the minus 60, I think. And here's a picture of what that looks like. So this is phi at time t over 4 for solution A, which is right at the turning point of the bifurcation diagram. And the scale on the right here is now 10 to the minus 29. And energy on this thing was conserved to basically 30 digits. And you wouldn't be able to get that either if you didn't do the linearized version of the Jacobian. If you did finite differences, you'd be introducing errors in your Jacobian as well. All right, so I'm probably dwelling on numerics too much. So what happens if you go to finite depth? Now you have a bottom wall to help push the jets up. So you get larger amplitude waves. Basically, the height, the maximum height here ends up being bigger. And the other thing that happens when you add finite depth is that there end up being a lot more resonances, where somehow the depth is sort of getting involved in the requiring that the thing be time periodic. And so I want to try to explain what I think these disconnections in the bifurcation curves are. I skipped over that earlier, but like if I jump from this branch here to this branch here, what basically happens is somewhere in here there's a resonant mode, which means that if you linearize the problem about one of these solutions, the linearized problem, there's a solution which it nearly satisfies the linearized problem with zero boundary conditions. So it's like an eigenvalue problem where there's just some solution of the homogeneous problem. And so although it doesn't exactly satisfy, I mean, you'll get an actual bifurcation instead of one of these sort of approximate bifurcations, which does happen if there's an exact standing wave that does that. But what happens usually is that there's just an approximate resonant mode, and it ends up being excited at one of two possible amplitudes. And if you're on one branch, it has one amplitude. If you're on the other branch, it has the other one. And usually what that means is that there's this higher frequency standing wave that can either be in phase with the main wave or out of phase with the main wave. And depending on which branch you're in, that's the situation. So here's a movie of one of those standing waves where you have a standing wave on the standing wave. This is the one where the sort of at the peak, the wave, the new standing wave causes an even higher jet of fluid. So this, as far as I can tell, is always what happens in these disconnections, is that there's just some new mode that would like to be on top of the wave that prevents you from being able to solve the equations without it. And it gets amplified a lot because, sort of like if you're doing linear algebra and the matrix is almost singular, the solution will generally have a very large component in that direction of the null vector, or of the almost null vector. So that's the same sort of thing that happens here. You get close to a resonance, you'll end up with these new standing waves appearing. And I would say that's why I see those oscillations in the limit in the other case as well, is that there are just these modes that aren't very strongly controlled anymore by the equations, and they have to take pretty large coefficients in order to, when you actually do the minimization. I'm sure I'm running out of time, but so I've also looked at quite shallow water. This is So here what I'm trying to do is like try to construct something that are like solitons, but for full Euler. So this is an exactly time periodic solution. I've scaled vertically by a factor of 150. So that's why these particles look like they're bouncing balls instead of an actual fluid. Anyway, what I think is interesting here is that you have this background required standing wave that needs to be there for this thing to end up being periodic. So let's see. And in the shallow case, you end up with a lot of these disconnections. And the higher Fourier mode you look at, the more they are there. And I'll try to say something about resonance in a second about this. But anyway, this is a kind of a different picture than we saw in the case of the deep fluid, because the shallowness introduces a lot of new resonant possibilities. All right, so here's one of the wildest solutions I've gotten. This guy, so I've only scaled this one by a factor of 15, and when this wave meets this wave, they actually sort of almost splash up, but not in a singular way, in a nice controlled way. And actually the splash is higher than the depth, so that's a very large amplitude standing wave. I figured this thing was terribly unstable, and we were talking about this the other day, and so I tried, the last day or so, I had the computer run this over 100 periods to see what happens, and weirdly, it wasn't unstable. I mean, it still agreed with the initial conditions to about 12 digits after 100 periods. So if it is unstable, it's only mildly unstable. So anyway, that was in double precision as well. And here's the error of that last solution at time t over 4. So that's how many, each dot represents a grid point. All right. So what's going on with those resonances? So I don't know. But here's an analogy that I can make. I've started to think about KAM theory a little bit and small divisors on systems where people have already figured out how to do this. And so I just looked at this nice system. Ulla Hall wrote a paper about this in 1974, I think, with this particular system. I think Arnold had something like this in mind too when Kolmogorov, Kolmogorov, I don't know exactly what he was thinking about planets, and then Arnold thought of a simpler problem than planets to study resonances in small divisors. So what you're doing here, you have a very simple system. It's a mechanical system, 2 wheels rotating. There's a weak spring connecting them. There's various parameters, the moments of inertia and so on. If I write this system in terms of sort of a first order system, I introduce phi as the angular velocity, and then you can write it in this way. So what you do in this KAM theory is you look for quasi-periodic solutions by sort of you assume that theta and phi, which are like your Hamiltonian angle and momentum, are basically moving along straight trajectories in the torus, and then there's some sort of perturbation u and v that you have to define on that torus to make them actually satisfy this equation. And so your goal is to find u and v so that this equation, so that theta and phi by this equation will actually be a solution of this problem. And there isn't really time to explain this at all, but I just wanted to say you can take the equations here. You can introduce an epsilon, which is k. So if the epsilon 0, that means there's no spring constant and the wheels are just going to spin. So that's the integrable case. We're in a nearby situation. So introducing epsilon, the equations of motion end up looking like this. The derivative, or the rate of change of the solution along these characteristics ends up satisfying this equation. The epsilon's here. If you just set epsilon to 0, it's really easy to solve the system. For the scalar case, it would look like this. This is the standard way of doing KAM. You expand f in a Fourier series. You see what would have to happen for this equation to be satisfied by the solution, and all you'd end up having to do is divide by these omega k plus j's that come up. And then if omega is sufficiently irrational, they stay away from 0. Omega k plus j stays away from 0. And the Fourier coefficients of f decay faster than these guys grow. So you can end up with a solution of this. I'm doing a shooting approach, which nobody does this for KAM, but I thought it was kind of cute to try taking my method and applying it to KAM theory. And the same kind of thing falls out, but instead of doing Fourier modes in time and space, you just do Fourier modes in space, you have a boundary value problem in time, and you can write down what the resonant condition is based on those Fourier modes at the beginning. And so it turns out that you can just do KAM theory in one dimension less by posing it as a shooting problem. Like you pick the x2 variable as time, and then you write down what it would mean to be periodic that way. So anyway, what happens in the KAM world is if I solve that problem with the wheels, and I look at the first component of U, the kth Fourier mode of that, you end up with, I guess you can't even see these pictures very well, but the higher Fourier modes end up being more fragmented. At every rational number, you have these divergences. That's where you can show there's no solution. And higher frequency modes have more and more sort of problem locations, but they're smaller and smaller in amplitude. So this all reminds me of those solutions you see when you study Sobolev spaces, where you take, like, you enumerate all the rational numbers somehow, and then you take some singular function, but you put a tiny coefficient that's decaying, like 2 to the minus k in front of that coefficient, and then you sum something all up, and you end up with a function that's in L2. That's sort of the kind of thing that you're getting here. Like, you have all the rational numbers have problems, but the coefficients on those problems are so small that you'll never see them in real life. So maybe this is why you see these same things here, whatever this is, whatever these bifurcations mean. Higher modes, you have these further disconnections and so on in the period as the bifurcation parameter. I think it's very similar to what is happening in the KAM world, where you can actually analyze what the singularities are supposed to be. All right, so I should wrap up. Let me just say, I've looked at stability a little bit. These are flow K multipliers of the monodromy matrix. Up to point Z, they're all exactly on the unit circle to as many digits as I can compute, which is about probably 23 digits. Eventually, you start to have a couple of these guys sort of break off from the unit circle, and by the time you get to solution B, they are somewhat, there are several of them that are off of the unit circle. So by that point, they're starting to become unstable, which I think answers your question. That at some point on these large amplitude things, you'll end up with unstable solutions. I've done gravity capillary waves a bit. This is a solution where you basically have two of those Crapper waves going back and forth running into each other instead of the solitons running into each other. The problem that I worked on with Dave Ambrose was the vortex sheet with surface tension. Here we have two fluids, same density. There's an interface that has surface tension on it. I guess the colors here are pressure still. This interface actually does overturn, like right there. And we had to use the Howe-Lowengrub-Shelley formulation of the problem to allow for the interface to overturn for this guy. And I don't think I really have time to explain my 3D stuff. So let me I'll just show you, Chris did a great job with this. He parallelized this on the Lorentzium cluster at LBNL. So there's 500 million non-zero matrix entries. And anyway, you can get some really nice dynamics in the 3D case. And one of the problems we're interested in understanding is sort of like the pattern formation in Rayleigh waves and things like that. All we've done so far is sort of copied what I'm doing in the 2D case, and this is one of the solutions that he found. We're not, because I didn't know how to sum over periodic images, and I know that you can do it with Ewald summation. I just didn't know how. And the other thing is that, you would have to go to fast multipole, because if you have n squared things which have to interact with another n squared thing. So it's like n to the fourth, whereas here we only have O of n cubed. The matrix is sparse, whereas that was a dense n squared by n squared versus a sparse n cubed by n cubed. It just seems safer to go with finite elements. I regret it, actually, but that's what we did. And it's still fifth order in space and eighth order in time, so it's not a low order method, but we're running into issues where we don't have the spectral accuracy we need for our computations. All right, so I think that's it. Yeah, we'll stop there. Thank you.